Welcome back. In our previous episodes, we've dived into the details of models like BitNet, Diff Transformer, and Instruct-GPT. Each of these approaches focused on different aspects, like scaling efficiency, noise reduction, and human-aligned training, core challenge. But one core challenge persists across them all: managing memory and computational load, particularly for long sequences. So, today, we're rewinding a bit to revisit FlashAttention from 2022. Core challenge. Even though it came before some of these newer developments, it addresses these very challenges head-on, with a unique focus on I/O-aware memory optimization. This makes it a pivotal piece in understanding how to make these models not just bigger but faster and more efficient.
That's a good point. While newer models have made strides in scaling and alignment, the underlying memory bottlenecks still slow things down, especially when sequences get long. It sounds like FlashAttention's principles could offer valuable insights to enhance these newer models as well.
Exactly. The paper we're discussing today isn't just another optimization attempt, it introduces some game-changing ideas. FlashAttention brings I/O-aware attention to the table, aiming to optimize memory access, which has been a major bottleneck in traditional attention mechanisms.
And let's not forget the speed factor. It achieves up to a 7.6x speedup, particularly on long sequences, which is quite impressive for exact attention.
It's not just about speed, though. The algorithm also excels in memory efficiency by avoiding the creation of large intermediate matrices. This means memory usage scales linearly with sequence length, which is crucial for practical implementation.
Plus, it has that block sparse extension, right? I remember it further reduces memory use and speeds things up for really long sequences.
Absolutely. And that's not all. By enabling longer context modeling, FlashAttention directly improves model quality, whether it's through better perplexity scores or performance on long document classification tasks.
So, in short, we're looking at a model that doesn't just optimize one aspect but brings together faster computation, better memory handling, and enhanced model quality, all at once.
That's the essence of it. Today we'll be breaking down the key mechanisms of FlashAttention, exploring how tiling, recomputation, and block sparsity contribute to its efficiency.
Sounds good. I'm excited to understand how it achieves such a balance of speed and memory efficiency.
Great! Let's jump into the details and see how it all works together. All right, let's look at the abstract of the paper titled FlashAttention: Fast and Memory-Efficient Exact Attention with I/O Awareness. It begins by highlighting a major challenge with transformer models. Their time and memory complexity increases quadratically with sequence length, which makes them slow and memory-intensive when processing long sequences.
I see. So the focus is on making transformers faster and less memory demanding, right? But how have previous methods tried to solve this issue?
Good question. Previous methods aimed to reduce the computation complexity using approximate attention techniques like sparse and low-rank approximations. But here's the catch. These methods often compromise on model quality and still fail to achieve real speed-up in terms of actual processing time, known as wall clock speed.
I get that. So they were focusing more on reducing the operations without considering memory access, which is equally important for overall speed.
Exactly. The authors argue that a missing element is making attention algorithms I/O aware, which means accounting for the data transfers between the different levels of GPU memory. This is a key factor in speeding up attention computations, since GPUs have fast but limited on-chip memory, and slower, larger, high-bandwidth memory, HBM.
Got it. So how does FlashAttention address this issue?
FlashAttention tackles this by using a tiling strategy that minimizes the reads and writes between GPU HBM and on-chip memory. This means it processes smaller blocks of the input sequentially, reducing memory access and avoiding the need to materialize the entire large attention matrix in slow memory.
So it keeps as much computation as possible in the faster memory, right? And does it lead to a significant speedup?
Yes, exactly. The results show that FlashAttention achieves up to 7.6x speedup over the standard PyTorch implementation for attention, with much fewer memory accesses. It's optimized for a range of sequence lengths and achieves both faster execution and lower memory use compared to standard attention.
That's impressive. Is this method only for exact attention, or does it also work for approximate methods?
Great question. Flash attention can also be extended to block sparse attention, which is an approximate form. This extension is even faster, achieving 2 to 4x speedup over regular flash attention by processing only the non-zero blocks in the attention matrix.
That seems like a versatile solution. And besides the speed up, does flash attention also impact the quality of the models?
Yes, it does. By supporting longer sequence lengths, flash attention improves the quality of models. For instance, it enables better perplexity scores on language models like GPT-2 and boosts performance in long document classification tasks.
So, in short, flash attention manages to achieve faster training, better memory efficiency, and improved model quality.
Exactly. It not only speeds up the training of models like BRT and GPT-2, but also extends their capabilities, allowing models to handle longer contexts more efficiently. All right, moving from the abstract, let's dive into the introduction of this paper, which sets the stage by discussing the role of transformer models in popular applications like natural language processing and image classification. As these models evolve, they've become larger and deeper. Yet integrating longer context remains a challenge due to the quadratic time and memory complexity of the self-attention mechanism.
So, the core problem here is that while transformers are scaling up in size, handling longer sequences efficiently is still a bottleneck, right?
Exactly. Even though models have advanced in many aspects, the self-attention operation's quadratic scaling with sequence length makes it very resource-intensive. This has motivated researchers to seek ways to make attention faster and more memory efficient, especially for long sequences.
I remember that approximate attention methods had been tried before, like sparse and low-rank approximations. But it seems they didn't achieve widespread success. Why is that?
Great recall. You're right. While these methods do reduce computational and memory requirements to linear or near-linear complexity, many of them still don't provide actual speedup in terms of wall clock time. This is because they focus mainly on reducing flops, floating point operations, but often overlook memory access overheads, which play a significant role in performance.
I see. So, the problem isn't just about reducing operations, but also about how data is moved between memory levels, like the fast on-chip memory and slower main memory?
Precisely. The paper introduces the concept of I/O awareness, which involves accounting for memory reads and writes across different memory levels in GPU architecture. This principle aims to minimize slower memory accesses, while maximizing the use of faster on-chip memory, particularly in the context of self-attention.
That makes sense. So, the main goal here is to optimize memory access to achieve better real-time performance, right?
Yes, that's the idea. By optimizing for I/O, the proposed flash attention algorithm avoids unnecessary data transfers, making attention computation faster and more efficient. This focus on memory access efficiency is a key differentiator from previous methods.
It's interesting how the focus shifts from just computation to data movement as well. It seems like an essential shift in perspective for deep learning on hardware.
Exactly, and this shift is crucial for modern hardware where compute speed is outpacing memory speed, making memory access a significant bottleneck. By addressing this bottleneck directly, flash attention aims to support longer contexts in transformers while still achieving faster processing and lower memory usage. Now, transitioning from the broader background of flash attention, let's focus on its performance on hardware, specifically GPUs. The authors of the paper provide a detailed look into the GPU memory hierarchy, which plays a crucial role in understanding how flash attention achieves its speed and efficiency.
Right. I remember that GPUs have different memory types, each with varying sizes and speeds. How is this relevant to flash attention as performance?
Good point. The GPU memory hierarchy is composed of several layers: on-chip RAM, registers, and high-bandwidth memory, HBM. Smaller memory, like on-chip RAM, is much faster but more limited in size, while larger memory, like HBM, is slower but has a greater capacity.
So, for Flash attention, to be efficient, it needs to make the best use of this fast but small on-chip SRAM, right?
Exactly. The speed and efficiency gains of flash attention largely come from its ability to exploit this memory structure. Since operations on GPUs can be either compute-bound or memory-bound, the arithmetic intensity, a measure of the number of computations per memory access, determines whether an operation is limited by computation or memory access.
That makes sense. So, if the operation has more computations relative to memory access, it's compute-bound. If there's more memory access compared to computations, it's memory-bound.
Precisely. Flash attention aims to minimize memory-bound operations by optimizing memory access. It uses techniques like kernel fusion to reduce the number of times data needs to be moved from slower HBM to faster on-chip memory, which is especially important in memory-bound operations like softmax.
I see. By merging multiple operations, kernel fusion can avoid redundant memory accesses, right? But how does that specifically help in the case of flash attention?
Yes, you've got it. Flash attention applies kernel fusion to combine several element-wise operations, such as dropout and softmax, into a single kernel. This minimizes data transfer and helps maintain most computations within the faster SRAM, reducing I/O complexity.
And this optimization would naturally contribute to better runtime and memory usage, especially when handling longer sequences, right?
Exactly. The efficient use of on-chip SRAM allows flash attention to support longer sequences and still deliver significant speedups compared to other attention mechanisms, even for sequence lengths up to 64K. Now let's transition into the standard implementation of attention, which is the baseline flash attention aims to improve upon. In this context, we're dealing with the computation of attention over input sequences represented by matrices Q, K, and V.
Okay, I know that Q, K, and V refer to the query, key, and value matrices, respectively. But what does the process involve for these matrices in standard attention?
Good question. The process involves several steps. First, the dot product of Q and the transpose of K is computed to form a matrix S, which captures the similarity scores between each pair of elements in the sequence. Next, the softmax operation is applied to S to obtain matrix P, which represents the attention weights. Finally, the output matrix O is obtained by multiplying P with V.
So, each step involves matrix multiplications or element-wise operations. How does this translate into memory usage?
Yes, and this is where the main challenge lies. Each of these steps, computing S, applying softmax, and generating O, requires writing intermediate results to high bandwidth memory, HBM. Given the quadratic nature of the attention mechanism, this can lead to substantial memory usage, specifically big O of n squared, where n is the sequence length.
That's quite memory intensive. I can see how this becomes a bottleneck, especially for longer sequences.
Exactly. And because many of these operations are memory-bound, meaning they involve more data movement than computation, the runtime of the standard implementation can be quite slow. This is further exacerbated when additional operations like masking or dropout are applied to the attention matrices.
So, standard attention is not just heavy on memory but also on processing time due to repeated memory accesses?
That's right. The frequent reads and writes to memory slow down the overall computation. To mitigate this, previous attempts have been made to fuse multiple element-wise operations into a single kernel, which reduces redundant memory accesses. However, even with kernel fusion, the standard implementation still struggles with the quadratic scaling in memory accesses.
I see. So, the problem is not only the quadratic complexity but also the inefficiency of data movement during computation?
Exactly. And that's one of the main reasons flash attention was developed, to minimize these costly memory operations by keeping more computations within the faster on-chip memory, reducing the need to store large intermediate matrices in HBM. All right, moving into the core of the flash attention algorithm, this section focuses on the main innovations: tiling and recomputation. These techniques are used to reduce the number of memory accesses when computing attention, aiming for subquadratic memory accesses.
So, Tiling and recomputation are the keys here. How does tiling work in this context?
Great starting point. Tiling breaks down the input matrices -Q, K, and V into smaller blocks that can fit within the faster on-chip memory of the GPU. The idea is to load only these smaller blocks into on-chip's RAM, process them, and then write the results back to the slower high-bandwidth memory, HBM, as needed.
That makes sense. It's like working with smaller pieces of the puzzle one at a time, so you don't need to handle the whole large matrix in one go, right?
Exactly. This approach not only reduces memory traffic, but also improves numerical stability during the softmax operation. Softmax is applied within each tile, and the results are incrementally accumulated, ensuring that the overall output is correctly normalized by the end of the process.
How about recomputation? It sounds like it might involve doing calculations again, which seems counterintuitive.
Good observation. Recomputation indeed involves recalculating some values, but it's a trade-off to save memory and of the forward pass. Instead of storing all intermediate matrices, FlashAttention keeps only the final outputs and the softmax normalization constants. This allows the algorithm to recompute intermediate results as needed during the backward pass, which uses less memory overall.
I see. So, recomputation helps avoid storing large matrices in memory by recalculating them, making the backward pass more memory efficient.
Exactly. Even though this increases the total number of floating point operations, flops, it significantly reduces high bandwidth memory accesses, which are the main bottleneck for runtime.
So, by reducing memory accesses even at the cost of more flops, FlashAttention achieves faster computation overall?
Yes, that's the essence of it. The reduction in memory traffic far outweighs the additional computation, leading to better performance. This I/O-aware design is what allows FlashAttention to run up to 7.6 times faster than standard attention implementations, even with longer sequences. All right, transitioning into the analysis of I/O complexity for FlashAttention, this section emphasizes how the algorithm optimizes memory access, specifically by reducing the number of high bandwidth memory, HBM, accesses compared to standard attention.
So, the main focus here is on how FlashAttention minimizes memory reads and writes, which is crucial for faster execution.
Exactly. The analysis shows that FlashAttention achieves significantly fewer HBM accesses due to its efficient use of on-chip memory, primarily through the tiling strategy we discussed earlier. For comparison, while standard attention requires theta of n times d plus n squared HBM accesses, FlashAttention reduces this to theta of n squared times d squared divided by m, where m represents the size of on-chip memory.
I see. So, the number of HBM accesses is much lower because FlashAttention keeps more operations within the faster SRAM, right?
Precisely. This reduction is crucial because the runtime of attention operations is typically dominated by memory access time rather than computation, especially for large sequence lengths. By minimizing HBM accesses, FlashAttention not only improves speed, but also reduces memory usage.
And I assume there's a theoretical limit to how much we can reduce HBM accesses with exact attention, right?
Yes, that's correct. The paper provides a lower bound on the number of HBM accesses for any exact attention algorithm, showing that it's impossible to asymptotically improve beyond what FlashAttention achieves for a given range of SRAM sizes. This theoretical limit further emphasizes the optimality of FlashAttention in terms of I/O efficiency.
So, does that mean FlashAttention is as efficient as it can get for exact attention with current hardware configurations?
Exactly. The analysis concludes that FlashAttention is nearly optimal within the constraints of existing memory architectures, making it one of the most efficient implementations for exact attention available today. All right, moving on to a key extension of the FlashAttention algorithm, we have the block-sparse version. This version is designed to work with approximate attention by focusing only on non-zero blocks of the attention matrix, reducing computational and memory overhead.
So, instead of computing the full dense attention matrix, block sparse, FlashAttention only processes the relevant parts determined by sparsity.
Exactly. The algorithm uses a predefined block sparsity mask, which specifies the non-zero blocks to be computed. By skipping the zero blocks, it achieves fewer memory accesses compared to standard flash attention. This extension makes the attention mechanism faster and more memory efficient, especially in cases where sparsity is inherent to the data.
That makes sense. But how does this affect I/O complexity compared to the original flash attention?
Good question. The I/O complexity of block-sparse flash attention is reduced by a factor proportional to the sparsity ratio denoted by S. For instance, while the original flash attention has an I/O complexity of theta of n squared times d squared divided by m, block-sparse flash attention scales it down to theta of n squared times d squared divided by m times s, making it even more efficient.
So, the greater the sparsity, the better the performance in terms of I/O.
Precisely. As the sparsity increases, the runtime improves proportionally, since fewer memory transfers are needed for the non-zero blocks. For large sequence lengths, the I/O complexity can be reduced to levels like theta of n times the square root of n, or theta of n times log n, depending on the sparsity pattern applied.
Is there a specific type of sparsity pattern used in the experiments for block-sparse flash attention?
Yes, they use the fixed butterfly sparsity pattern, which is known to approximate arbitrary sparsity effectively. This pattern allows block-sparse flash attention to achieve significant speedups while maintaining performance close to that of dense attention.
And how does it perform compared to other attention methods in benchmarks?
In benchmarks like the long-range arena, block-sparse flash attention achieves up to 2.8x speedup while maintaining competitive accuracy. It performs faster than both exact and approximate attention implementations for longer sequences, demonstrating its practical efficiency. Now let's explore how flash attention helps achieve faster model training. The authors present results showing substantial speedups across popular models like BRT and GPT-2.
I see. How significant are these speedups compared to standard attention implementations? That's impressive. What about GPT-2? Does flash attention deliver similar improvements there? And what about longer sequences? Does flash attention manage to keep the efficiency gains there too? So, flash attention not only accelerates training, but also allows for handling longer contexts, improving model quality.
Now, transitioning to how flash attention contributes to better models, this section highlights its impact on handling longer sequences effectively. The main idea is that by enabling longer context lengths, flash attention not only improves model speed, but also enhances model quality in tasks that benefit from more extended context.
I see. So, extending the context length leads to better results in models like GPT-2 and long document classification tasks, right? That's impressive. It shows that longer sequences do make a difference in language modeling performance. So, flash attention really makes it possible to use more context in models without running into memory or runtime limitations. It seems like this makes flash attention a game changer for applications that deal with long sequences.
Yes, it opens new possibilities in sequence modeling by making longer context feasible in both training and inference. It's a significant step towards building more effective models for tasks that demand comprehensive understanding over extended input sequences. Now that we've covered the improvements flash attention brings to training speed and model quality, let's dive into the benchmarking results. This part of the study measures runtime and memory performance across different attention mechanisms, comparing flash attention and block-sparse flash attention with various baselines.
Got it. So, how do these benchmarks compare for sequence lengths, memory usage, and runtime? That sounds efficient. How does flash attention compare with approximate attention methods like lint-former or local attention? Interesting. So, block-sparse flash attention maintains its edge across a wider range of sequence lengths? I see. And does flash attention's performance vary based on hardware, like different GPUs? That makes sense. So, the memory optimization really helps it maintain performance across different devices.
Now, shifting to the limitations and potential directions for future work, the authors highlight several key challenges that remain with flash attention and its implementation.
I'm curious about these limitations. What are some of the main ones discussed? That sounds like a major engineering hurdle. Does this mean the current implementations might not be portable across different GPU architectures? Interesting. So, Making the implementation process more accessible and flexible seems to be a priority for the future. I see. So, the idea is to make the entire deep learning model more memory efficient, not just the attention part. That makes sense. Using multiple GPUs could add more complexity but also more opportunities for efficiency gains.
Multi-GPU parallelism would require new techniques to manage the data transfer between GPUs, which would be another promising area of research. Overall, these limitations and directions highlight the scope for broader advancements in iodine monoxide-aware deep learning, beyond the current capabilities of FlashAttention. Well, that wraps up our deep dive into FlashAttention. We've covered a lot today, from its I/O-aware design to the tiling and block sparse extensions that make it so efficient, especially for longer sequences.
Absolutely. The way it balances speed and memory efficiency really stands out. Plus, seeing its impact on both training speed and model quality gives a lot of perspective on why it's still relevant today, even with newer models around.
Exactly. And as we continue exploring advancements in scaling and alignment, understanding these foundational innovations is crucial. FlashAttention shows us that optimizing memory access is just as important as scaling up model parameters.
It's definitely a great takeaway. I'm excited to see how this approach might inspire future developments.
Same here. And to everyone listening, thank you for joining us. We hope you found today's discussion insightful.
Yes, thanks for tuning in. Stay curious, and we'll see you next time.